Thank you, participants, and on behalf of the organizing committee of at IIT Tirupati, FDP on additive and smart manufacturing for biomedical applications, I would like to invite Professor Ram Kumar sir for this invited talk. Before I start his talk, as a protocol, and it's our honor to introduce today's speaker, Professor J. Ram Kumar, who is my supervisor also. So let me introduce formally. So Professor Ram Kumar has been experience of more than 2 decades in the research, academia, and industry. He has been influential in developing the tremendously accurate micro nano machining process, which have been an integral part of the current age defense systems in the development of metamaterials for the defense technology, unmanned air vehicle, machining process for aerospace and missile parts such as components and shells used in man-portable anti-tank guided missiles. As a researcher, he has focused to use his knowledge and expertise to employ sympathy studies to cater the unmet needs of the deserving people, has enabled aggressive technologies in locomotive and visual disability to overcome the architectural barriers and tools for the agri-tech. Since his inception at IIT Kanpur in 2003, his journey of research has been employed good teaching and learning practices with an ultimate motive of coalescing research and academics in the innovative manner so as to develop the solutions which increase the efficiency of the products and pose minimal damage to the environment. Imaginarium Lab, Tinkering Lab, Makerspace, MedTech Lab, and RUTAC, Rural Technology Action Group at IIT Kanpur, are all his brainchilds that provide an ecosystem to cater to the requirements of needful users to be its students, scholars, faculties for the project work across the country. He has been mentored and nourished more than 15 startups spread across the nation who had been exceptional in providing novel products and have stepped up into the market. Professor Ram Kumar, sir, is a frugal innovator with a deep interest in manufacturing sciences, and in the trying names of the COVID brought many innovations which are used in Pan India, like Swasa masks and Sanjeevani oxygen concentrator were a blessings for the front runners and hospitals. He has been brought out 8 MOOCs courses having more than 48 lakhs views, including international audience, conducted and organized 100 plus workshop in the area of design, thinking to propagate science and research among the students, scholars and industrial participants and faculties. Owing to his indigenous and in situ contributions, it would not be an overstate to say that Professor Ram Kumar's name is now synonym to the manufacturing engineering in the research community. With this tremendous short bio, I would like to now request Professor Ram Kumar sir to take over the invited talk of today. So thank you, sir. And
Professor Ravi, thank you so much. See, it is always good to see the son growing up more than the father. So I was really happy that Ravi is flourishing so nicely, and Ravi is trying to connect with lot of people. So I am very happy. So thanks, Ravi, for giving us an opportunity to meet such a elite community of people. See, all these people, audience, have taken break in their busy schedule. After 7:30 when they reach home, they try to connect with this course. This shows their urge for knowledge. So I should be thankful to them, thankful to Professor Ravi for organizing this wonderful event. And I also would welcome you all for my talk. So with this, let us get into the talk. So I would request the audience that you might have a lot of questions as and when we roll down in the slides. So please try to put it in the chat box. As and when something comes to your mind, keep dropping it in the chat box. End of the lecture, I will try to answer as much as I can best possible. Suppose if the question is tough, I could not answer, then I will take that question and I will reply to the organizer, Professor Ravi, and Ravi can share it with you. Okay. with that small brief, good evening, and let's get into the topic. So today I am going to talk about multi-material 3D printing. See, we know rapid prototyping, which is otherwise called as 3D printing, is gaining lot of momentum. Why is it gaining lot of momentum? Because we are today looking for mass customization. When we look for mass customization, what should be the typical batch size? The typical batch size should be 1. So that means to say, no two products will be same, they will be similar. Then you might say, why are you talking about so much? Because if you see in reality, very, very rarely you see two people identical. Even in an identical person, you have thumbprints which are varying. So that means to say every person is unique. So if such is what is the customer today, then why should our product not be unique? So keeping this in mind, rapid prototyping came into existence. So it was initially thought of rapid prototyping, and as and when the maturity started happening to the process and people started exploiting and exploring the process more and more and more, the terminology slowly moved from rapid prototyping to rapid manufacturing. What do you mean by rapid manufacturing? Rapid manufacturing means whatever I produce, I can directly put into real-time use. So that is rapid manufacturing. So now slowly, rapid prototyping is moving towards rapid manufacturing. What gets printed from the machine can be directly put into real-time usage, be it defense, be it aero, be it auto, be it biomedical. Every place you are now trying to print it and place it to make the customer comfortable with the product. So when we look for strength, then we always try to go towards metal-based additive manufacturing. When we look at high temperature application, then we move towards ceramic based application. When we are looking for non-structural, and if you are looking for biomedical, then we move around predominantly polymer based printing. Till now, the market was very, very open for printing of single kind of material. For example, you take ABS wire, PLA wire, you take PC, you take these are all these things if you take in FDM process. If you move towards powder-based process, SLS process, you think of again ABS, polycarbonate, nylon, Teflon. You try to think of all these things, you will see that all these print material will be only one kind of material. Slowly, people have now understood how to mix two wires and generate new colors. But the world, what it wants is multiple material should be able to print in one single layer. So that is what is my focus for today, wherein which I have given it as multi-material 3D printing, which is exhaustively used in bioprinting. So this slides are being made by my student Prasenjit, and I on his behalf is presenting the slides. So the content for today's presentation, I will quickly go through introduction to 3D printing, then history, then some of the fabrication processes, then application of biomedical field, application of 3D printing in biomedical field, then working of multi-material printing, what are the different stages of 3D printing, then design and additive manufacturing file formats, comparison of different file formats used in 3D printing, then applications of multi-printing in different segments, 4D printing, challenges and future scope. So when we talk about rapid prototyping, it predominantly starts with only 3 different types. It can be either powder-based, It can be wire base or it can be liquid base. Okay. Of course, you have sheet base also, but sheet base is not having major applications today, except for few which are used in batteries and other things. Predominantly, these three players play a very, very important role. You start with this metal powder, ceramic powder, or you start with a polymer powder. The process predominantly goes around SLS process or SLM process. When we try to change the laser with glue, then it is called as deposition method. It is the glue will be deposited so that that will try to adhere the powders together. So it is called as inkjet printing. Okay. So when we move to extrusion, it is 1D wire is used. This wire can be a metal wire or a ceramic wire. You try to heat it and the wire is passed through it. If it is a metal wire, we try to create an arc and we try to deposit it, right? When we go to liquid, it is predominantly photopolymer based liquids, wherein which this liquid gets solidified by the activation of a blue laser. So it is very clearly seen from these three types. The best resolution can be obtained from liquid solidification, or where the starting material is liquid. Then comes extrusion, and then comes powder solidification, and the last one comes extrusion. When you are looking for strength, extrusion base is good. And when you are looking for large areas, extrusion based is good. When you are looking for small components, very good compaction, good strength, then powder solidification is good. And when you are looking for high accuracy and surface finish, we go for liquid based. So if you look into it, liquid solidification is SLA process, stereolithography. Extrusion is fused deposition model. Powder is SLM or SLS process. Rapid prototyping or 3D printing is a technique which is less than 50 years old. The first 3D printer came somewhere close to 1980s. Kodamo was the first printer which came into the market. Then came stereolithography in 83. Then the first commercial 3D printer which came in the market was in 86. Then close to 90, we had laser sintering based processes. And then in 2000, we had organ bladder printing, which started from 2000. And then moving forward by 2006, we had inkjet cell printer. Then by 2010, we had we had printed blood vessels, which was there by 2010. And 2015, we had drugs. First 3D printed drugs was there. And by 2019, we have the first 3D print lung and liver, which was done. So these are all the applications. When you move down and see, in 1985, we had SLA, DLP process, direct light deposition. DLP is, yeah, it is something like SLA process, right? So then you have SLA like TPP. TPP is photo cured resin. It's also an SLA process where starting material is liquid. From there, they move to SLS process, where in which you have nylon, PP, metal, and then FDM, which came in 1980s. So ABS, PLA, PC, PEI, all these things can be used. PEI are basically biomaterials. So the biomaterials can be melt cure polymer, natural hydrogel, synthetic hydrogel, DECM, and cell spheroids and tissue strands. So these are some of the materials, biomaterials, which came into existence from 2000, where printing could start. If you can see here, the first one where you have a nozzle seen, that is FDM printer. The next one, if you see, it will be inverse of SLA process, where it is called as DLP process. Then printing of organ was done again by FDM process. Then printing of artery and printing of lungs was done. So when we start this 3D printing in biomedical area, there can be two possibilities. One is you try to take MRI, CT or something like that. And then what you do is you try to do reconstruction of 2D image to 3D image. So 2D image for CT MRI will be taken by, this is computerized tomography, CT, and MRI is medical resonance imaging. Sorry, magnetic resonance imaging. So you try to take the detail, and these two, what you get is 2D, sliced information, cross section. And this, when we try to reconstruct it on top of it, you will try to reconstruct, and then you try to get a 3D virtual of it. So if you don't have a MRI or a CT, then the other way around is you try to have an organ. They try to do point cloud scanning technique. They scan it, and they scan it with laser, and the point cloud data is generated. Then from there, they try to convert the point cloud data into a surface data. So the 3D virtual model is done. So after this 3D virtual model is done, so first is you try to do the model, then you try to have a solid model which is watertight. Then you give all those informations towards the computer. The computer, what it does is it tries to slice the object, because then only it can construct layer by layer. From there, it is sent to a machine, and then finally the object is getting printed, and whatever is getting printed can be directly used, or it can undergo secondary process to put it into real-time use. So here are some of the applications of 3D printing in biomedical area. You can see that skin can be printed, tissues can be printed, organs can be printed, then cartilage and bones can be printed. Drug deliveries also can be done by using 3D printing. So when we try to talk about a typical application of a human here, which I also underwent this process while working with a master student, we went through this complete process. It was a very good learning for us. See, first was we did magnetic medical imaging by CT or MRI, but in this case, in our case, we had a we had a laser reverse engineering tool. So from the reverse engineering tool, we could develop a CAD model. So we used a laser. So the laser will try to collect all the data. So whatever data is collected is called as point cloud data. With this point cloud data, we converted into a surface, and that surface we try to tessellate. Why do we tessellate? Because tessellation tries to tell where the material is placed and how it is getting placed, and where is the material where there is no material. So all these things can be done by tessellation, which is STL5. Tessellation means it is just converting into small facets. All these facets will have a normal. So with this normal, you can try to see where the material is present or not. Then after this tessellation, we try to do the slicing. So once we do slicing, then the data is transferred to the machine. So visualizing motion program means here what we do is after the layer information is taken, now each layer will have information like G code, and it will also have feed rate. So we try to see how is it getting done. So that is what is visualizing motion program. So after that is 3D printing happens, and whatever is getting 3D printed, then we try to do some processing, and because of this processing, then they try to get into real-time use. So 3D printing is done here, and 3D bioprinting tissue products are seen here. If you see, it is interesting as compared to that of your ABS in FDM process or in SLS process. Here what you will have is you will have multi-material. So what are the material? You should have tissue, you should have cells. So all those things are there. So these things are all getting printed today. The scaffold and formation of the surrounding scaffold and tissue formation surrounding the scaffold, we can see. So the fabricated physical model gives the surgeon an ability to conceptualize the ideal course of action before surgery. Say, for example, if there is a surgery which is to be conducted here, so the the patient will first be done MRI and CT. He will try to understand, you try to reconstruct, and then he will try to see how do we approach this particular surgery and how do you do it. So printing, we can try to get a spongy bone, and then you can also try to have a compact bone. Then you will have a tabule, you will have this interconnects, and then you will have all these things done. So basically in bioprinting, what we do is we try to have cell plus scaffold leading to bone generation. So you will have a fiber here. Okay, so when we talk about this laser process, you will have SLS, you will have stereolithography, you will have fused deposition, and you will have the other process. So you will have the other process. So the next one is, so you can see it is not only the bones, but also the instruments which are used for surgery can also be 3D printed. So here it is metal is also used, and you can also use the polymers for various applications. So 3D printing physical model for surgery planning, you can see. So for the lower part, so they have identified, and then the doctor tries to access and see how do we access the part and how do we remove, what is the kind of operation we have to do such that he can be very, very successful. So for doing all these things, you will have to use multi-material printing. So first the virtual 3D skull model is done. Then the CAD 3D CAD design to the customized implant. So you see, maybe because of cancer, this is gone. So now this is removed, and they try to make a patch, right? And then this patch, what they do is they try to keep the patch and see 3D design for the customized implant. Then the patient specific skull model is fabricated, and then after that, the fitting of the patch is done by metal printing. So in the same way, this design and fabrication of customized vertebral implants via 3D printing is also done. A is MRI scan. Then we try to do implant design simulation is conducted. Then C, what we do is we C and D, we try to do virtual simulation of the implant. And E and F are are printed by Peak. So you can have this also for hip joints. You see here. So design and fabrication of hip implants. You can see lateral view. A is the lateral view. B is the meridian view, medial view, and then you can have an outer view and then backside view. So if you are looking for generating an organ, it goes like this. First, you slice and get the image, slice image of the CT scan of heart valve. Then a CAD model is generated. A 3D printing is printed on the biomaterial. Then the 3D printed heart valve mold is made. Then they made a scaffold. Then they make tissue engineering around it. Then they make 3D printed heart valves. Then bioreactors. And finally, what they get is tissue engineered heart valves they get. So these are the steps which generally undergo when you are trying to prepare the heart valve. So first CT, CAD, 3D printing, and then 3D printing or bioprinting. So this is a typical bioprinting of an organ which you can see from this diagram. Then you try to get a scaffold, tissue engineering and other things are done here. So base design, and this is the arrowhead design. You can see vascular stents. Vascular stents are being made today. Earlier, these stents used to be made by laser, and now they are trying to make it through rapid prototyping. So they have base design and they have arrowhead design to do the CAD. Then they go into fabrication. So in fabrication, I showed you an inverse of getting printed. So it happens like this: UV light is exposed. So you will have the liquid polymer there. So in the liquid polymer, you try to develop that light, and then it's a liquid polymer. The liquid polymer, one layer by layer by layer information is done, and then you drag it above. The platform is pulled up. So then you try to get the stent and then UV. So you also have O2 to permeable films also can be generated in this. So every time when the light is exposed, you have single layer of information. These are the products which are made out of stent. So this can be used for real-time application. It can be used for real-time application, and this is for customized cervical orthosis. So this is 3D scan. So first is A is 3D scan, B is geometry of orthosis, and then C to E is design optimization. See, the best part of rapid prototyping is not exactly printing it and taking it into your into the real-time use. You try to do optimization. And based upon the optimization, you try to get, so we can try to get many things. So this is what is 3D printing or the orthosis. And here what we do is there is something called as topology optimization. This topology optimization, it tries to reduce this thing. Okay, so they try to reduce, and then they try to get the reduce the unnecessary material present. So it tries to remove material, so it makes it lighter, it makes it thinner, it makes it stiffer. So you don't have to fill material everywhere. So that is what is design optimization. So there is an exclusive field where people are working on topology optimization of additive manufactured parts. Then comes 3D printing orthosis. Then you have G is orthosis padding cutting, where variational surface cutting algorithms are used. H is final the cervical orthosis by assembling the printed components they used to take place. So additive manufacturing is done, then padding is done separately, then they get the final orthosis. So you see here G is the pads which are made after cutting, and then you get the use. So bioprinting and functional skin also can be done. So this is where there is a multi-jet printing happening. You will have collagel. In this, you will have collagel. You will up and down, you have collagel. Then you will have fiber blasts which are there. Then you have fibrogens. You have, and then you also keratinocytes also you have. So all these materials, cell, everything will be mixed in a liquid form, and it will be allowed to pass through a nozzle. So the tool used for dentistry, you can see these are the tools which are metal printed, and it is used in dentistry to retain the gum. So selective laser sintering process, which is basically we use a laser, and you have a metal powder or a ceramic powder or a polymer powder. We try to pass a laser on top of it. The laser basically does a sintering process. Sintering means it does not melt it completely. The powder is consolidated. Powder is consolidated, and then you join each other. So selective laser sintering is a process which is done. And then so here you try to develop, you try to join those metal powders, and that process is called a selective laser sintering process. So when we are trying to talk about printed copying of cobalt chrome, this is also done by SLS process. So the scaffolds, whatever we have made, these scaffolds are done very nicely. The drilling is done, the screws are printed. The screws, there are multiple threads. One is like you have front butterworth and then reverse butterworth, and then we have a mixture of front and reverse butterworth. We have a straight grooves made. All these different types of threads are there. So now after rapid prototyping coming into existence, such kinds of multiple threads can be synced and overlapped in one metal component. So that helps while inserting the teeth, gets very firm and tries to give a lot of resistance for shearing action. So the defective areas, after tooth extraction, then the scaffold was placed in the dental side. Progress of the implant is made, and then you try to get this thing. So once you try to get everything, the chrome cover is made, and then they try to do it. So this is a machine wherein which they try to print ceramic crown, and they also have a possibility of printing metal. When we are trying to talk about materials of bioprinting, you will not have a single material. That's what I said. You will not have a single material. You will have a mixture of multiple materials. So for example, polyethylene glycol can be there, polyvinyl alcohol can be there, collagen, polyurethane, then argine, then you can have gelatin, asparagus acid, then you will have gelatin. So many materials are used for making organ on a chip. When we talk about biochemical assay and screening, we use so many things. So here it is not one material. This is where the challenge is multi-material. When you try to use multi-material, the viscosity changes. So once the viscosity changes, the pattern changes of deposition. Once there is a pattern changes, there can be a shrinkage variation. Moment there is a shrinkage variation, that leads to defect. Okay, so this makes the life miserable. So you see here, inspiring mimetic. So you'll have functional design, then applications, you'll have scaffold design, lab on chip, medicine, micro vessel, and then you will try to have artificial things. These are all the gelled cell printers which are there, where in which you try to get the output. So multi-material 3D printing, how does it work? The fundamentals of 3D printing system is to use physical means of depositing material through nozzle of a to a specified position at a given rate at a given sequence. A typical printing process of multi-material or heterogeneous object printing is shown in the figure 1. So the subsystem will have 3-4 nozzles, and all these nozzles will be operated independently. All these things will be operated independently. When they are operated independently, you try to get proper deposition of this nozzle material on top of a table. So you have this thing, and here the biggest challenge is all these nozzles. If you have a liquid material, so then they will have a plunger type. Through the plunger type, they try to push the liquid, and that gets deposited on top of a table, and then you try to cure it. So typical printing process of multi-layer or heterogeneous object printing is you will have these nozzles. So you will have varying things flowing in this nozzle. So when you try to look at this, I have already discussed it. So product design, image of an object and physical model. So 3D the digitization, point cloud data. So that comes from reverse engineering. So that reverse engineering comes from surface model. So you get a model, then volume model, then you do triangulation, basic model, slice contour algorithm, and then what you do is you have a 3D printing process and the object is printed. So these are all the different stages which are used today. So tessellation is nothing but a triangulation, basic models, slicing process, and the contour data. When we try to look at the additive manufacturing in the modeling side, you can directly use a CAD model or you can use a point cloud data. So when you use it, they convert all these things into STL file. And the STL file gets their input from two informations. One is called as geometric information. The other one is called as topological information. So these two informations also are trying to get stuffed into STL model. So whatever is there in the STL model, then there will be always refinement and optimization of mesh and face it. So that will be the next step after getting the STL model. So here also what they do is they try to get the functional requirement and also the design requirement. Functional requirement and design requirements are completely different. Design, so functional requirement means, for example, in your hand, finger plays a very important role. Design requirement is, so you have the bones inside, all these bones can be one, but they are converted into linkages. So that is a design linkage so that you get the flexibility of it. So refinement and optimization of mesh is done. So that data is also given after the STL is made. From there, what they do is they try to go for color HEO model. So colored HEO model, till now, what we are seeing normally is single color. So here, after this, they will try to have a colored HEO model. Then the data is given for processing. When we look at material feature, the material feature database, the material information, and then you have geometric information, then you also have topologic information. So these three are very important, and they get all this information. If you see here, one is geometric information. So the other one is topological information. When you say geometry is shy shape. Topology means it tries to give the XY coordinate points also. So material information, geometric information, topology information, all these informations are very much required. So then we have this. So taking all these things into account, now what we do is they try to use this for 3D printing. So when we from the model side, we try to see model orientation. So model orientation also plays a very, very important role. So this plays a very important role, and this is this model orientation, and because of that, the supporting structure is also done. So model, why is the model orientation? The strength of the component depends upon the model orientation. So you can try to do it vertical, you can try to do it horizontal, you can try to do it at an angle. So model orientation is important. From that model orientation, they try to hit it and try to reduce the supporting structure generation. And then the model slicing happens. Then after the model slicing happens, parameters like speed, rate, feed rate, contour path, all these things process parameter design, then only the file gets generated, and then you see the process simulation, and then it is sent for printing. When we are trying to talk about this control and mechanical subsystems, you see here control systems will have all the nozzle, mechanical systems will have from that nozzle you try to exit through this nozzle and go. So these are all the challenges, and till now additive manufacturing, whatever we use a format and wherein which we don't have the color as one of the objectives. So when we try to look at basic structures of additive manufacturing file format, you see objectives. Each file must contain at least one objective element to describe the objective. Then material single or multiple material IDs for printing. Then you will have single print as a defined single or multiple texture mapping. And then you will have the multiple displays. You will also have defined displays parameters. This display parameter, rotational parameter, all these things are there. Okay, so this is one. So now when we are looking at formats, you have STL format, OBJ format, and PLY format. So the description is basically STL format has in terms of triangular patches, vertices, color values. When we talk about OBJs, they will try to have straight line, polygon, surface, freeform curves. When we talk about PLY format, vertices, faces, related data, and groups, all these things are there. So this makes the file size large or small. This makes the error reduced when we are trying to use multiple materials. So when we try to talk about design of additive manufacturing file format, the technology independent will be AMF. AMF is additive manufacturing file format, uses XML structure to describe the information. It can be not only processed by computer but also human understandable things. So AMF format is nowadays very much talked about. The new standards not only records a single material but also assigns different materials of different parts and can be changed. It is possible to simplify an image to be printed on the surface of the model. Raw data such as author's name, etc. can also be recorded in the technology independent AMF files. The simplicity makes this file very important. So when we are using two different types of material, then all these things play a very, very important role. So it is extendable, it is high performing, and it is strongly compatible. So these are some of the advantages. If you try to look at various files which are available today, so you have STL as triangle, OBJ, PLY, AMF, and 3MF. All these things are there. Whether STL will give an option for color? No. PLY gives you an option for color. AMF gives you an option for color. 3M gives you an option for color. Whether it contains material information. If you see, AMF contains medical material information, and 3MF also contains medical information. So which are all the companies which are trying to do? AFM is done by ASTM committee, and 3FM is done by 3D manufacturing committee. So from the CAD model visualization operation, a heterogeneous part can be made. Say for example, you see here when you try a monochromatic part printing, so the STL file which you can see in the A, which is monochromatic, but when we try to convert it into B, you see here the color STL file is there. So the color STL file tries to give you better visualization and also give you a better understanding. So the CAD model of heterogeneous part cannot be directly designed by commercial softwares. So therefore, the color models are generally applied to represent different material distribution and in order of facilitating visualization operation. Right. The different 3D printing technologies which are available today, we have seen all these things. So when we try to take granular material form, direct metal laser sintering, electron beam melting, selective laser melting, selective heater sintering, all these things are there. Powder jet spraying is that binder jet spraying. Whatever I say, instead of laser, if you replace it by binder, it is binder jetting. Then you have loam in this process. So the three-dimensional printing has various applications which we have already seen. So these are some of the applications which 3D printing is in indirect production of monolithic catalysts. So you can see here all these things can be made, catalyst can be made. So A and B 3D printing polymer matrix. C is a matrix filled with ceramic. C is a matrix. See, first is A and B are polymer based. C is the matrix which is filled with ceramic. Now they remove the polymer and now what they have is only ceramic. A catalyst support after removing the matrix is seen here. Then a catalyst with deposition of activated phase looks like this. So what I'm trying to convince you is that if you are looking for something like electrodes, which are to be made for some application, so you can start using it like this. Make a mold from 3D printing in plastic, then you try to fill it up with ceramic, then you try to remove the polymer. So the commonly used printing of heterogeneous components these are the things which we have already seen. So when we talk about heterogeneous components of 3D printing, costs have decreased, development cycle is shortened, application range is heterogeneous. So you have various applications which are there. So today when we talk about 4D printing. So 4D printing refers to intelligent material printing structures from the basis of 3D printing. So both structural and functional changes can be made over a period of time. So 4D is this. So you have 1D. 1D is a wire, 2D is a plane, 3D is a cuboid, and 4D is something wherein which you try to activate it with energy and other things. So 4D printing refers to the intelligent material structure from the basis of 3D printing, achieving its structural or functional change. 4D printing material are intelligent material. There can be smart structures. By the application of external field, you can try to distort or change in structure or do anything with respect to the object. So that is what is 4D. So you can change it by light, you can change it by pH, you can change it by concentration. You can change it by electromagnetic field, temperature field, etc., etc., etc. can be used to change. So the intelligent material structure possesses several features imitating the biologies such as self-prolifilling and self-healing, self-diagnosis. All these things are nowadays things done by using 3D printing. So this is okay. So the intelligent 3D printing, then the intelligent material structures possesses several features imitating this, and 4D applications of aerospace vehicles are also thought of today. So when we try to do 4D printing, you can see that the client is scanned three-dimensionally. So then the customized dress is designed on computer. Then the design is tessellated. Then so if you see this is pretty interesting. Now what they do is if you want yourself to undergo some X-ray exposure or if you want yourself to undergo a light exposure, now what they do is they try to fully take a image of you, then they try to make a dress for you. In that dress that tries to protect the body from getting exposed to that light or X-ray, and then they try to ask you to wear, you wear it and then you try to do it. So in the same way you see your client is scanned three-dimensionally, customized dress is designed on a computer, the design is tessellated into triangles, whatever we said, kinematic structures is generated using an interconnecting segment. So this interconnecting segments will make the dress lighter and lighter and lighter. So this concept is also used for 3D printing of biomedical. Okay, this thing, and then what we do is we try to this thing, and then 5 is draft is simulated. Draft is draping means covering the body, just trying to overflow on top of the body, just like a tight dress, tight baniyan. Okay, then the dress is compressed through simulation, allow 3D printing to create it in a single assembly, and then you try to stretch it. So this is what is the capability of 4D printing, which people are now talking about. So 4D printing is additive manufacturing printing. Then you will have smart materials. So 4D printing is such structural design can be done, and you can also start doing the mathematical modeling and simulation of it. When we talk about smart materials, the response to heat, the response to light, all these things, response to heat, response to light, response to moisture, electric field, magnetic field, all these things come into existence. So this is and then the next one is pattern printing, hinge and this thing hinge and geometric origami approach is also used. When we talk about mathematical modeling here, instead of pixel, we try to talk about a concept called as voxel. We try to have so then we will try to have a box-based model and a simulation approach. Simulation approach can be done. So this is there. So voxel means volume pixel is called as voxel. So voxel-based modeling can be done, and then that. So all these things get into 4D printing. So you have to do so much of printing and then getting it done. So when we are trying to do this 4D printing, now 4D printing is exhaustively used for biomedical printing. So what they do is they try to activate the things from outside by field, by electric field, by pH change, temperature, humidity. So these are the polymers which are available, and these are the output responses which are available. These are the applications. These are the applications which are there. So this can be done. So you will try to have the output response, the swelling contraction, viscosity change, electric signal, capacity resistance, force, all these things are output responses which can be changed based upon the input stimuli, whatever you give. So these two tries to bring in applications. And so artificial muscle can be printed. Then you can try to have this thing like arms, tissues. All these things can be done with use of 4D printing. So what are all the big challenges? The big challenges which are there is customized desire of products in short time is the biggest desire. Then producing of biocompatible products such as organ or replacement tissue is also very, very important. Next is non-requirements of storage of goods is there. Say for example, here you don't have to store as and when you require, you try to build material to your requirement. So creating objects, complex objects shapes otherwise mean impossible to create in conventional, that can be done very easily. For example, if you want to have fins, cooling fins, which has to be done around the nozzle. So that can be done very, very easily by using this 3D and 4D printing. And this 3D printing and 4D printing is cost effective. So if you look at the 3D printing, so this is a cycle which it undergoes. So you will, so if you see there, this is called as the hype cycle of 3D printing. So according to the hype cycle of 3D printing, what does it say is the 3D printing is already at the highest point now. So it is peak for inflation is expected. So after this, it is expected to fall down. But if you see 4D printing and other things, they are all in the innovation trigger. They are all now trying to move towards the 4D. So the 3D printing retailing will slowly fall down in the trough of disillusionment. But if you see the 4D printing is going to move from innovation, it will be start moving towards the positive. So the plateau will be reached. The plateau, the toppest point will be reached. If you take 4D and all, in more than 10 years only it will reach. When you try to take about this 3D printing in oil and gas and all, it will take another 5 years. If you are going to try to do other normal printing, it will try to go much faster. So this is a hype cycle which is created. So this is to be taken with a word of caution that 3D printing is gaining a lot of momentum and is also reaching its top. So if you look at the future scopes, improvement of feedstock material is something which is still not there. So feedstock means multiple material mixing. Reduction in temperature and post-processing is another important thing. So printing techniques can improve the resolution. So the control of porosity can be done. Better control and acid-based and redox-based catalyst is also thought of today. And optimization of the catalyst design is also playing a very important role. So with this, I will try to stop my presentation. But before I would take questions, I would like to share and show you some videos. So kindly bear with me. I will play some videos for you. Okay, is my screen visible? So this is the latest bioprinter which
Yes,
they
sir.
have developed. So you see these parts, whatever it is given here, this is getting printed. So you can see such printing, such this thing can be made, cells can be made, and they can start placing it. So all these things are now they are trying to do with this bioprinting. So I will show these are all porous structures. This porous structure is used for getting integrated into the body. So I will show you some more. So is this screen visible?
Yes, sir.
Okay. So here you see that these are some of the prints which they are trying to make. So okay. So this is how the printer looks like for bioprinting. So you see here, these are all the nozzles I told you. These are all multiple nozzles. Sorry. These are all the multiple nozzles. These are all the different fluids which are there. This will have cell, this will have colloidal, all these things will be mixed here. So you can try to have cell only in one, colloidal in the other. So now what will happen is this, you will have to control each one of the fellow while it is getting printed. So this is what is a challenge in bioprinting or multi-material printing. So you see here, they print the complete organs. See, this is how the bottle they fill with all the reagents and liquids, whatever it is, organ, which is later printed into organs. So you can see here it is printing. How nicely it is. It is just like your FDM, but the viscosity is to be controlled. The surface tension is to be controlled. So these are the challenges which is going to be there for 3D printing. You can have heterogeneous material. It will not only be fluid, it can be anything, right? So this is the challenge for this printer. So this is something, okay, I will show you some more videos. So this is upcoming field, and a lot of new things are happening, and the completely this domain is new. So all these things are nowadays bioprinted. Let me show you only the video. See, look at it. So 3D printing. So now whatever you saw was getting activated. No, so this activation is done by 4D printing. So you can stimulate it by changing the pH, or by changing the chemical composition pH, or by electric field, or by whatever it is temperature. You can do it. So you can see. So this is how the printing happens, just like your FDM, but the viscosity is different. So now you see these cells are deposited, and then they try to functionalize it. So this is a developed function of, so now you see they print it. So the organ are not yet realized, but there are a number of encouraging projects which are coming. See, this is how the printing happens. And now you see here, whatever nozzle we said. So this is for the ear printing. This is for the finger, whatever they made. So now they are, after the printing directly, they are trying to use it for as like rapid thing. This is a skin printing which is going on, scaffold printing. So you see now all these things are getting printed, and here it is multi-material uh, approach. It is not a single material approach. So here they don't talk in terms of wire, they talk in terms of ink. So they call it as bioprinting ink. Okay, these are some of the research which is going on abroad. So people have printed the Irish, people are printing organ. Okay, so these are some of the things. See, these are small organs which are already been printed. This is printed inside, and this is already, it is printed inside. Otherwise, it will not be stable. So these are some of the things which is up there. So you can see the changing viscosity. This is for the year. So these are something which is very interesting, and a lot of people are working on it. So I will one more video I will show. With that, I will try to stop and take questions. It's too small. This is for heart printing. So many electrodes go. So many electrodes go while doing operation. So see, this is artificially printed. Human heart model. They are artificially printing it. It is very flexible. The material is very flexible. Now this is only a covering. So inside this is the covering, and now this has to be activated from outside. So when you have to activate it from outside, you have to use for something like a 4D mechanism. So look at it, they are trying to do regenerative biomed therapeutic group. Carnegie Mellon has developed this. So they are trying to figure out what is the strength and how does it move, what is its response. Okay, so this is also printing. So you see here it is print of material B. Then you will have a, so now you see the strength of it. They also try to see what is the strength of the skin, what is the strength of this thing which they use. So you can see here it gets peeled off at the location itself. So you can print all the MRI scan. Then you print a 3D heart. Then through that they also try to do try to fill in with fluid and see how the response is, what is the time it takes and other things. So with this, I would like to stop my presentation and I would be happy to take questions. There are, okay, so there are questions online. Okay, these are all no questions related to the talk. So now it is open for questions. If there are audience you want to ask, you can go.
Yeah, thank you, sir, and for your valuable presentation and on especially on 3D printing for the biomedical applications and so on. So now the audience or presenter, I mean say participants, you please introduce yourself first to the speaker and you can ask the question. So now it's open for you. You can take your time for one by one. There is no hurry or something. Just one by one you can raise the hand and one by one you can go ahead. Thank you.
Yeah, please go ahead. I'm just playing you the videos where you see how the printing happens of 3D.
Good
Yeah,
evening, sir.
please go ahead.
Hello, sir. Good evening,
Yes,
sir.
go
Yeah,
ahead. Yeah,
go ahead,
good evening.
Kishore.
Sir, this is Kishore from Good Love Engineering College, Vijayawada. Sir, my question is, what are the methods to control the porosity for the scan folds?
So see, when we are talking about medical field, the pores are going to be intentionally introduced. Here they will not look for zero pores. They would look for pores so that the blood flow can happen, the cells can grow, the integration of the foreign body can happen into your body. So here we would always look forward for porosity in the part.
Yes, sir. Yes, sir. That's why only this porosity plays an important role for the tissue development.
Yes.
Is there having any methods to control this porosity or any other methods to develop a different types of structures for the porosity?
See, structures of porosity, basically what we do is we do something like topology optimization, and we also try to see how the flow happens to it. So basically the porosity, whatever you do, it depends upon the viscosity of the fluid, biofluid, and it also depends on the hatch pattern, whatever you choose, right? So with this, you only have to come up with something.
Yeah,
So
yeah.
in
So,
metal, when you talk about the porosities must be avoided. But here, what happens is they would look forward for this thing for porosity mixed. And here we don't talk about micron accuracy. So here the deviations are millimeter wise. It is also okay for us.
yeah,
Okay.
sir, one more question, sir.
Yes.
Is there having any FE structural analysis for scaffolds? I mean, a deformation or stresses
Yes,
bearing to
yes.
the loads, FE
See,
analysis.
now there are a lot of library functions which are getting integrated in the finite element analysis itself. But still, for deformation of scaffold and other things, it is still not very well established. So
Yeah.
people, what they do is they try to take the properties, they try to draw, randomizely generate pores. They try to take the properties physically measured. So they try to develop it like a semi-empirical model, and then they validate the results.
Yeah. Thank you, sir.
Okay,
So one more question, sir.
please.
Actually, I forgot it. So
Okay, you can.
I will ask other some other time, sir. Just
Else can ask and then you can see. So you can see here, uh, so this video, whatever I'm playing is again for an organ, right? You see here, finally, you had 47 ml of liter of fluid flowing through the organ. It is 4 milliliter per minute or something. Go ahead.
Sir,
Go
sir.
ahead.
Yeah, yes, sir.
You can go ahead, Professor Kishore, you can ask him.
Yeah, okay, sir. Thank you, sir. Sir, is there having availability of bio inks in India, sir? Laboratories, bio inks.
No. See, it is expensive. Currently, whatever comes, we are only, majority of them we are trying to import. Few of them in India have started, but that is not so very popular. So
Any locations, sir?
it is all
3D bio
imported.
printings.
I don't have, no, bioprinter are there in IIT Kanpur, it is there in AIIMS, it is there in, it is there close to you. I don't know whether Hyderabad, IIT Hyderabad has it, but there are almost all the medical schools are nowadays having it. AIIMS has it.
Including IIT Tirupati, we have.
IIT Tirupati bio printing is there.
Yeah. Okay, sir. Thank you,
It's
sir.
expensive. The fluid is expensive.
We would like to say that we are in the developing the bio inks.
Yeah. Thank you, sir.
The bio inks, whatever we develop, the only thing is it gets settled down fast. So the USP of the company, why is it expensive? Is the Brownian motion still is there such that the cell keeps moving. Even in nanofluids, what happens when we develop in the lab scale, it gets deposited at the bottom after some time. So that is what is a big challenge for developing these inks. Anyhow, Professor Ravi is developing it. So you can.
We are developing along with our past batch of IIT Guwahati. So we have Vimal Katiyar group and other people. So we have collaborators from Japan actually, from Kyoto and other people. So we have a biomaterials group, which is including Kyoto and Tokyo and IIT Guwahati and IIT Tirupati. So, but as myself, I consider it as lowest version because we don't have much expertise, but we are in the group and sometimes we take from them, sometimes we develop, but what we develop is for orthopedic and derma. We are not into the cardiovascular or so on. So that much advanced level we don't have. But some knowledge that we have is on orthopedics and derma. That's all. So we are not expertise in cardiovascular or say nerve or something. Okay. That's just.
Yeah. So this is what, see, you see that this is all lungs, airbags.
Yeah, this much knowledge we don't have.
So this is what it is, and these inks are pretty expensive, and it is still in a long way to go. So here, this is what I said in the beginning. Do you remember? I said for drug delivery. So for drug delivery, they make capsules, and in the capsules they have this medicine, and they try to push it into your body, and they are able to track it where the medicine goes. How does the medicine react? So for that capsule also they make. So here you see that, okay, if you see the previous one, you see that magnetic field is applied and it tries to pull the liquid. You see the next one. So this is magnetic field. It is trying to apply and it is trying to pull the fluid flow. So this is a upcoming area, and good that you are. I think Tirupati has a vision. They have taken this as a topic. Printing 3D bioprinting is the latest.
Yeah, as I said, though, we are in the basics of like derma and orthopedics.
Yeah. So see, bio inks. These are all bio inks. And is it like ABS? You get it? No. You don't get it like ABS. See, ABS, you go polycarbonate, you buy it in the market. Now, PLA, you buy it in the market. Elastomer, you buy it in the market. But here, it is not so. Okay, any other questions from any other audience?
So there are some inks, commercially available inks that you can also procure like PEG-D and other things.
Yes.
These are all like PCL, PLA, PCL, PDM. Yes. So there are many varieties are there. Actually, see, you should know, Kishore, I think, no, you are from Gudlavalle. Yes, I'm telling you. So
Yes, sir.
there are some PEG-D based, there are some other PCL based, and normally these are all multiple polymer blended based actually. But normally, at our institute, we study about rheological aspects mostly because our area of expertise is rheological aspects. So we work in that hydrogel based, and most importantly, you should have some knowledge about extracellular matrix and other things.
Yes, yes.
Thank you.
Sir, thank you, sir.
May I, sir?
Yeah, please go ahead.
Good evening, sir, Professor Ravi sir and Kiran sir, to give this opportunity to meet eminent person in the field of manufacturing and additive manufacturing processes, sir. So very good evening, Ram Kumar sir. This is Dr. B. A. Naidu, student of Professor Akshay Dwivedi from IIT Roorkee, sir.
Ah, Akshay, a student. Okay, okay. Go ahead, go
Yes,
ahead.
sir. I have met several times, sir, and actually every time you are surprising with different topics, sir. I have met in 2018, you surprised with additive manufacturing with metals, and I met you in 2022, sir, and you have given some kind of knowledge with physics, which is related to the defense system recently. And this time, yesterday, I had this doubt, sir, multi-material printing. I had discussion with PK Jain, sir, and Ravi, sir, also. And today you have cleared most of my doubts, sir. Thank you so much for that. And my question is that actually I have some plan to print some bones, sir, like human bone printing, sir. So I need some suggestions.
Is it foam or bone?
Bone, sir, bone. Sorry, BON.
Yes, yes. Go ahead, go ahead.
So I have a thought like if you have kind of any means bone and if you can crush it in a powder form, so can we go with a printing like centering like kind of thing, sir, with the 3D printing?
Okay.
So is it feasible? I have just thought, sir. Is it feasible? Can you give some insights?
Naidu, you go to Tirupati, right? You get
Yes, sir.
Balaji Prasad Laddu. See, the bundi alone, if you have, that does not mean that you can reconstruct the laddu, right? You
Yes, sir.
need binders.
Yes, sir. Yes, sir.
These binders are going to play an important role. And second thing, if you try to take a bone and crush it, what you
Yes,
get
sir.
is hydroxyapatite. But this hydroxyapatite, you have to blend it in a binder, and that binder should flow. And when it flows, the flow should have uniform dispersion of volume fraction of hydroxyapatite.
Okay.
So crushing it is not a big deal. But
Yes, sir.
crushing
Yes, sir.
it with a liquid, that liquid should flow, and when it flows and when it cures also, it should be the same. See, when it cures, what should happen? All the polymers should get off and
Yes,
all
sir.
the hydroxyapatite should stay there, right? So when the hydroxyapatite should stay there, polymer should go up, then you have to go for a sintering. So when you go for sintering, then there will be a shrinkage. So it is a big loop.
Yes, sir. Sir, I mean, in like
Yeah,
what? Yes, sir. Carry on, sir.
Yeah, you carry on. You carry on.
Sir, same thing is when we get the powder form of any kind of bones, with the help of 3D means 3D printing, sir, like with laser, can we do that, sir?
No, see whatever you see, what you can do. See, and if you take bone also, Naidu, it is not 100% densified. So
Yes,
if you
sir.
see the skin of the bone, it is thick. Then if you move further inside towards the core, you will have coarse grains, coarse shells will be there. See,
Yes,
these core cells, so where in which the volume fraction changes. So based upon the change in volume fraction, the toughness happens. See, now if you wanted a broken bone is there, rather than reinforcing it with ceramic, if you try to reinforce with metal, that is much more better.
Okay.
See, people have started using the egg shell. They took the egg shell, they crushed the egg shell, mixed the egg shell with something, and they printed it. But finally, after all these things, they did not get the property close to the bone.
Okay.
So SLS also, when you try to join it, it cannot be polymer. Now you have to go ceramic. So you have to go to very high temperatures.
Yes, sir. Yes, sir.
Crush it, egg shell they take, they crush it, they start doing it, but it is far-fetched, Naidu, and it is not taking us to the right route. Until and unless you have a good strength property, you can't try to go on. So I would suggest that is not taking us anywhere. If you want to have a small coating on top of a bone,
yes, sir,
or a metal surface, you want a small coating to be done. where in which you wanted to have all these bone characteristics, then yes, you can try to do something like a cap,
Okay.
where it is possible.
Sure, sir. Thank you, sir.
And there also you should have polymer inner coating so that the friction is reduced. I think one of the speaker from Gandhinagar, she will be speaking, or he or she will be speaking about this tribology, biotribology. There you will see this polymer, all these things play a very, very important role.
Tomorrow is the talk by Professor Harita from IIT.
Okay.
Sri Harita.
Sri
Yeah.
Harita, sir. IIT.
She will be talking on biotribology. I mean, say ceramic implants, and it is tribology.
Sir, what I feel that if you implant any metal, our body feels it's a third person, like it won't treat as its own material, sir. So in that way, I am thinking.
Yes, yes. See, even today there is
always it's a foreign material. If we treat as a foreign material, and again it will react to our it, sir.
Yes, yes. See, even today there is no proper literature which is available. What the steel implants, what we are doing now when a broken bone
Yes,
is
sir.
there.
Yes, sir.
The steel will always react with blood. So if it
Yes, sir.
reacts with blood and some chromium, all these things get released. What is the influence on the human performance is still not studied, because all these things to study you need 10 years, 20 years, 30
Yes, sir.
years.
It's a longer time. Yes, sir.
Longer time. So still this is not, it is not very much accepted. See, slowly, we will try to get out of these inserts. But as
Yes,
of
sir.
now, we are in the boon of getting into inserts. But later, somewhere down the line, these inserts will go.
Okay. Thank you, sir. Thank you so much.
So you are in which college, Naidu?
Sir, now I am as assistant professor in Centurion University, Orissa, sir.
Acha, Centurion University, Orissa.
Yes, sir. Orissa.
Okay. Good. You did on ECM, right?
Yes, sir. ECDM, sir.
ECDM, correct.
Yes,
Right.
So there is one Centurion in border Andhra also, no?
Andhra also, sir. Yes, in Vijayanagaram also they have one campus. In Orissa they have 4 campuses, sir.
Where are the other campuses in Orissa?
Sir, one is in Bhubaneswar, one is in Parlakimudi, and one is in Raigada, and one more in some I don't know exactly the remember. I didn't remember, sir. So
okay. Andhra, this is Pallakmudi, na?
No, sir. Andhra is in Vijayanagaram, sir. And this
Proper.
Parlakimudi, what you are saying is border of Andhra Pradesh, sir. That is also commander Orissa, but it's border of Andhra Pradesh.
Fine, thank you. So you are in
I
Orissa.
think you came last time, sir, here as a speaker, sir. P.S. Rao, sir, said.
Yeah, I came online.
Yes, sir, online, yes.
Thank you. So you are in Orissa or you are in Andhra?
Orissa, sir. Parlakimudi.
Okay.
Parlakimudi.
Where P.S. Rao is there?
Yes, sir. Where P.S. Rao is, sir.
Thank you.
Thank you, sir.
So other people?
Good evening, sir. I'm Srinivas Kumar, sir. Hello.
Yeah, please go ahead, Professor.
Yeah.
You introduce
Sir,
yourself.
the this
Can you
3D
introduce,
printing.
Professor, can you introduce yourself and ask?
Yeah, I'm Dr. M. Srinivas Kumar from Nasaraopet Engineering College, sir.
Okay.
Sir, this bio material will have a different material, sir. Any part, as the sir said, even a bone consists of a different porosity, parameters, etc. All at a time. Can we do it on one machine, or it has to go in a different machines, sir? 3D printing machines.
Sir, it is always good to have in a single machine. So in a single machine, how can you have multiple things? You should have multiple nozzles.
Yeah.
So now you have to control the flow through the nozzle, multiple at different locations. It has to drop.
Okay.
Currently, FDM goes with one nozzle or two nozzle. One fellow is on, the other fellow is off.
Okay.
In this, what happens? Both the fellows will keep printing, and it will be on a single machine.
Okay.
Because it is almost like a gel, sir. This gel also will solidify, and when you go layer by layer by layer, you have to introduce material in between also.
Okay. In case of FDM is okay, sir, but in case of SLA, I think only one material only can do.
Correct. SLA is only one material. Now that is what they do is they use the process FDM. Instead of a solid wire, they try to use a semi-solid liquid.
Okay, sir.
And there is a syringe, something like a syringe. Through that syringe, they control slowly and then push it inside.
Okay, sir. So is there any demarcation that this 3D printing process is for this type of bioprints and this FDM is for this type of bio products, like that? It will be any demarcation is there, sir?
Nothing, sir. See, based upon the requirements, nowadays they tailor make the machine, sir. For
Okay,
example,
okay.
today,
Yeah.
if you instead of
Yeah.
ABS, you try to use elastomers, you
Yeah.
can print flexible dies, molds.
Yes, sir.
So depending upon your requirements, they try to tailor make the machines little bit, sir.
Thank you, sir. Very informative, Ram Kumar Garu and Ravi Shankar Garu. Thank you, sir. Nice arrangement, sir. Thank you, sir.
So if any other questions from any other audience?
Any other questions, please? Otherwise, we'll wind the session.
Because it is already very late for your dinner.
Yeah.
No?
Yeah. So thank you all the participants and thank you, sir. So
Thank you, Ravi. Thank you, Ravi, for organizing. Ravi, you're still in the office. Huh? I have gone home.
yes, sir. Yes, sir. I am at office. Okay. So thank you, sir. And on behalf of me and on behalf of my colleague, Professor Kiran, so we both are the organizers and co-organizers, or you can say both are organizers only. So on behalf of IIT Tirupati, I extend thank you to you, sir, for your valuable information that you have passed on to our participants that enhance their knowledge. And more importantly, that our people are active and asking multiple questions. Thanks for the people who are asking questions and which enhances other people's knowledge also. So with these short words, I would like to say thank you to the speaker as well as, and please participants come online. Tomorrow you should not say that our attendance is missing or not. We are taking your attendance at the various levels and somebody raised the questions saying that examination will be there because we have to follow the ATAL rule. We cannot have our own rules or something. We have to follow AICT norms. You have online online FTP is there first week and second week you have offline. So you have to undergo the test for online, you have to undergo the test for the offline both. Okay, so this is the information that we got from the ACT. So don't think that in a negative way or something. Just it is our, we are here to pass on the whatever the rules that they are there. Just we are here to implement those things. Okay, don't fear that there is examination or something. No. So if you sincerely listen, the basics only, we are going to ask you the basics. So please attend and more importantly learn as much as possible. That is most important. And I think Professor Ramkumar also emphasized the same thing. Just don't look at the marks or something. How much you learned, that is most important for us. Thank you.
Thank you, Ravi Garu. Thank you very much, because it's very convenient time without affecting our college works. I think a nice timing, sir. Really, it's a wonderful. Though we are busy at college, we cannot do it, but you made it possible to attend and learn these so many things.
Yeah, thank you. And I wish all you people should come to IIT Tirupati and enjoy the hostel life because
We will, sir. We will. We are waiting. We are waiting to.
so you will have to enjoy the hostel life because we are providing you preferably independent rooms but in a hostel because as you know IIT Tirupati is younger institute and we are working hard. Our team is working hard to make you comfortable. So please be here and try to book your out back on Saturday evening because Saturday we are going to visit some industry because industry visit is part of this course. So Saturday morning we are going to some big industry which is one of the world best industry that is situated in India. Okay, so which supplies components to Apple mobile and other things. Okay, so preferably we are negotiating with them and they accepted for our invitation and we are working for that company. If possible, we are going to visit another company which is a sister concern for Honda and other places also. So hopefully we will make you some at least industry visit where you can get some knowledge on some of the manufacturing intricate aspects. Thank you with this. And I wish all the people to, and I request all the people to join on time. That's the only request from my side. And on behalf of again IIT Tirupati, I wish thanks to my professor, Professor Ram Kumar. Thank you, sir. And convey my regards to your family members. Yeah, I'm more close to the family. So yeah, so that's why. Thank you, sir. Thank you all.
Thank you, sir. Thank you, sir. Thank you.
Yeah, Uday, you can close. Oh,
Okay.
yeah, so